everyone, and welcome to today's webinar titled Alarm Limits versus Trending. My name is Taylor Colon, and I'm a Customer Engagement Specialist here at TestOil. I will be your host today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure a high-quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer any questions that you may have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email you registered with. Let's get started. Today's webinar is presented by Evan Zabowski. Evan is a certified lubrication specialist and a senior technical advisor here at TestOil. Are you all set, Evan?
I am. Well, thank you, Taylor. So today's presentation, Alarm Limits versus Trending, is part of our data interpretation series. It's meant to help people understand how to interpret their reports a little bit better and possibly shed some light on the tips and tricks there are regarding what we do on our end and what you should do on your end. So I'd like to begin today's presentation with just a quick bit of history to show you where we've come from. Not we TestOil, but we, those users of oil analysis, to give you an idea as to why we are where we are today. So the quick history is that oil analysis was sort of first conceived in the 1940s, and it was the railway industry that thought the oil could tell them something about how their engines were running. By the next decade, we started seeing some military involvement, and we also started seeing some of the fleet involvement, mainly trucks, diesel trucks on the road. Once we started seeing some successes, the first commercial laboratory was opened, and thus began the industry that we exist in now. Now, why I give you this little brief bit of history is to show you where it's coming from. Now, those first people in the 1940s and 50s, what they had going for them was they were working with very large fleets. They'd have hundreds of locomotives, hundreds of trucks, all owned by one company. They had a very limited variety of OEMs. So saying that means that if you bought one brand of locomotive, chances are you had 100 of them. We also had very singular samples. We only took samples at drain. We didn't take samples while it was running. And we always took the sample from the draining oil, so the sample location was identical each and every time. The other thing that we had going for us was that each of these trains or each of these trucks or whatever it was coming out of had fairly consistent operating conditions, meaning it was always going up and down the same places, always under the same conditions or very similar conditions. And this would happen over the course of, say, many years, so we could smooth out some of those seasonal variances that we'd sometimes see. But the last thing I'd like to point out is that because this was in its infancy, there were very few labs that were running, because some of the labs were in-house, and there was, like I said, there was really only one commercial oil analysis lab for a while. And the end users, there weren't that many that were, taking advantage of this technology. So there was a very strong and direct relationship between these people. So what I mean by that is that every success that was achieved with oil analysis was shared and known by all, and every deficit that was encountered was again shared and known by all. So the labs could tweak what they were doing, and the end users could tweak what they were doing, and everyone could work together and make this a very positive program. So in today's world, we generally refer to it as big data, but given all the data that they had at the time, it was fairly simple for them to calculate these normal levels of wear metals and whatnot and figure out when and where to alarm them, because they would know that anytime that level had been exceeded was when they typically experienced some form of failure. But like I also mentioned, we could account for seasonal variations because we had tons of data to work with on a very consistent platform. So this is what we had, and I point this out and I make sure I speak to it in past tense because this is the history, and history often dictates the future. And where we are today is actually vastly different than where we began, yet we hold on to some really old ideals. And one of those ideals is alarm limits, and that's the point of today's presentation, is to try and move you off that concept that alarm limits are the way to interpret oil analysis. Trending is going to be the far more important tool to use, and I'll show you why. So where we are today, to run through that same list, is nowadays we have all sizes of fleets. We have one-offs and we've got big fleets. But even though we might have a big fleet, we have a much greater variety of OEMs and models. So even if we can narrow it down to a common OEM, there's now perhaps options. You know, when we think about certain types of components, there's reservoir size options, there's turbocharging on engines, there's higher performance options that we can add on to hydraulics and whatnot. There's lots of things that we do that start creating a greater variety, meaning you can't necessarily compare this one machine that looks like another machine because there might be some little difference between them that greatly affects what the oil analysis will look like. We also have started taking more samples. So we don't just take samples when we're draining the machine, we now take samples while we're running the machine. So we've got basically a moving target of what that oil is going to look like. We also have introduced a variety of sample locations because not everyone's going to sample from the same point, since there may be multiple options for where to take a sample. Some people might take it out of a drain, some people might take it on a filter manifold, some people take it on a return line, and all these different sample locations may affect what the results look like. But one of the key points now is that, oddly enough, we actually have a weaker relationship between the lab and the end user. Labs have grown substantially, and many labs have thousands of customers that they don't speak to on a weekly basis, and many end users treat the labs as a commercial service provider. They don't treat them as a partner in the reliability operations. So they send samples to the lab, they get results back, and they work from those results. Whether or not they experience a failure, whether or not they avoid a failure, they don't share that information with the lab, generally speaking. So the lab doesn't know if they're doing a great job or if they're doing a poor job necessarily. They only know that their end user is satisfied with the service. Now, one other thing I'd like to add to this list that wasn't on the previous list is that in today's world, the reality is this. Most commercial labs still receive many samples with vague information. So my example to you is something that's labeled Gearbox 101A, right? That is a end user name that gives the lab next to no details about the machine other than it's a gearbox. Oftentimes we don't get oil information, meaning we don't know what kind of oil is in there or how long it's been running or even how old the gearbox is. Sump volume's not provided, next to nothing's provided. And the funny thing about this situation is we are still being asked, well, what's an acceptable level of iron? Or what's an acceptable level of silicon? And in today's presentation, I'm going to try and show you how you can figure that out, because this is the problem we're faced with, and I know many end users are also asking these questions. So I'd like to hopefully answer that question for both the end users and those of us working in the oil analysis industry. So let's talk about sources of these limits. You know, we know they exist, we've seen them before, we've heard tell of them. They can come from a variety of sources. So the most common ones are directly from the OEMs, from your lubricant suppliers, and from industry. That's where you often see published tables with some limits being provided. Many end users, though, do rely on the commercial labs themselves to dictate what seems to be acceptable or what doesn't seem to be acceptable because they're relying on their experience. What I'd rather see is end users coming up with their own limits, and that's generally based on some type of goal. Are they trying to extend their drain intervals? Are they trying to extend their mean time between rebuilds? Are they just looking to increase overall uptime and reliability? Any one of these goals may dictate a certain type of limit or a certain interpretation of a broad set of data. Right? We can look at all the samples we've taken over the years, seen what works, seen what didn't work, and from there derive some numbers that might help us. But in the end, limits still have some inherent problems, and I'm going to show those to you as I give you examples of these various sources. Now, the first one I'll pick on is, here's one, a published table from an OEM. Now, I've not cited the OEM that's provided this table because I'm going to make fun of it and pick it apart. So it wouldn't be fair to put someone's name on this and make fun of them. But if you're looking at this slide, you may pick up on a major typo within this slide, and I have published this as it has been published on the internet. So this is not my typo, this is the original publication typo. But if you notice the title of this particular table, it is very wishy-washy. The first word in the title is suggested. Now, as soon as someone says suggested, that doesn't mean it's a recommendation that holds any water, right? It is not a specification that is an absolute. It's suggested. So if you happen to exceed it, it doesn't necessarily sound like there's a problem. They're only suggesting these are the ones you should use. The next word in the title is safe. So it's suggesting that if you are at these levels or lower, that is considered safe. But it doesn't necessarily mean that if you exceed these levels, it's unsafe. So suggested and safe are a very wishy-washy way of trying to give you a title to this table. But if you've read through this title, hopefully you've noticed the next line. I can tell you what 15 parts per million silicon might look like. I can quantify that, I can show it to you, I can give you a graphic on it. I could make 15 parts per million seem tangible and real to you. I have no idea how to make 15 parts per million natural gas engine look real though. But like I said, that's the typo that's in the table as it is published. Now the verbiage that comes along with this table, I'm going to show you now. And again, this is exactly as it was published. This is not my bolding. This is not my all caps usage. This is exactly how it's been published. So if you read the statement, it says these charts are for general use only. So right away, they're not meant to be used anywhere in particular. And then it carries on and says, and do not indicate definite limits of wear metals for any specific make or model. So in the opening statement, they're already trying to get out of you using these limits for anything in particular. What it goes on to say, what I actually value, says wear patterns are best established after evaluation of 3 samples taken at, and here's the keywords, the same oil change intervals. I'm going to dwell on that point a little bit later. But then it finishes by saying make, model, application, age, makeup oil added, time of use, or recent repairs can cause the values to vary greatly from those shown. So right away, they've given themselves the best cop-out possible by saying we haven't identified under which conditions this table works, and we're stating that any one of these variables, which are very common variables, will cause these numbers to be incorrect. So basically, they've said we've published useless data and no one should use it, and there is no good data out there. So why do OEMs publish these tables? Well, typically they use them to highlight major issues, things that are gone grossly away from normal operation and therefore need some immediate attention. Generally speaking, they're used to settle warranty claims. If you can show data that has remained within these limits, they might support your warranty claim. But if you show data that has exceeded these limits, that gives them a leg to stand on to back off and say, voids warranty. As I point out, they don't claim to represent optimal performance. It might mean adequate performance. It might last through the warranty period, but it doesn't necessarily mean you're going to see a long life on the machine if you maintain those limits. And the one last thing I'll point out, and this is a common denominator amongst most of the limits, is that they're generally implied to work on only those end of drain samples. You can't use the same limit on the running sample as you can on the end of drain sample because the end of drain sample has more time on it than the mid-interval sample. So we have basically samples taken across the entire length of an oil drain, which is a moving target, but we only have one limit to work from. And I'm going to point out how that's a bit of a problem. But to carry on with giving you some examples of where these come from, let's take a look at another OEM limit. Now this one I will qualify where it comes from. It's from Parker Filtration, and it's a pretty common way of phrasing this. If you read it, it says water contamination of engine oils in concentrations as little as 500 parts per million can seriously affect the oil's filterability and the function of the oil's additive package. So in that opening sentence, they claim 500 ppm could be problematic. They finish this quote by saying the detection of water in concentrations above 0.3%, which works out to about 3,000 ppm or 6 times more, warrants immediate corrective action and an oil change. So how do you interpret a statement like this? It says as little as 500 could be bad and 3,000 you need to act fast. Well, what this suggests to us is that we set our first limit at 500 and we set our second limit at 3,000. That's fair, that's fine, but that's a 2,500 ppm range where what do? Does it need immediate action or does it not need immediate action? It can seriously affect things, but doesn't need immediate action, that's kind of a contradictory statement. So like I said, you get some very wishy-washy terms being used with these OEM limits. So one of the other places we can look for limits is lubricant suppliers. And if you go to a lubricant supplier, and again, I'm not going to out them on this one, but this is a published online table of limits, and I've made no changes to it. This is exactly how it's been published. There are no typos in this one. But if you look at this, one of the first things I'm hoping that you notice is that they've provided limits for physical and chemical properties of the lubricant. They have not provided limits for wear or contamination like the OEMs did. So right away, we should hopefully notice that, because the OEM knows how the machine might wear. The lubricant supplier only knows the lubricant. They don't necessarily know what the metallurgy is in any one machine that they're going to possibly be using this oil in. So they can't really fairly address wear metals in their limits, but they can address contamination at times. But as you note, when they do address contamination, they're not talking about how much contamination the machine can tolerate. They're talking about how much contamination their lubricant can tolerate. So I'll take a step back here and say, I will be fair to them. Their limits aren't necessarily bad, not like the OEM ones. The OEM ones are they're horrible. But lubricant supplier ones, they have some credibility to them. I mean, when they talk about viscosity limits, well, it either is or it isn't in the correct grade. So that's fair to give a limit on that. When they talk about something like a soot limit, well, there is a threshold for how much soot an oil will hold before it starts to affect its viscosity. Similarly for fuel, there's only so much fuel we can dilute an oil with before it will affect its viscosity. So I can appreciate having limits on those particular properties. Now, when it comes to additives, they may address additives at time, but they're not confirming that that additive level means the additives are functioning. They're just identifying their product. So if you send in a sample and then get some bad results or bad performance from the machine, and you go back to your lubricant supplier and show them the data and say, look, your lubricant's not working. Well, one of the first things a lubricant supplier will want to check is if in fact you are using their lubricant. If there's any evidence of mixing with another product, well, they have, again, a leg to stand on to back off and say, well, we don't have to support you on this. Now, when limits are given for oxidation or other degradation properties, they are providing some sort of threshold there. They're saying that, yes, if you exceed this value or if you go below this value, it indicates the lubricant may not have optimal performance anymore. But you don't know under what conditions they come up with that number. And sometimes you might run under conditions that would suggest that's too early for an oil change, or you might run under conditions where it suggests that that may be a little late for an oil change. So again, you always have to take these limits as a starting point, whether they're from the OEM or whether they're from the lubricant supplier. Now, going to a different source, there's industry-specific limits, and this is one of the most widely cited tables in the industry. It's from ASTM. It's ASTM D6224 if you want to know where to get a copy of this one. But I've published it in its entirety here, and it's a pretty decent table. It covers a wide variety of tests, and it is sorted according to machine types. So we've got some pretty decent data here. But as much as people have used this table, very few people really read the full title of the ASTM standard. It's down there in the footnote, and I'll read it out to you. It says, Standard Practice for In-Service Monitoring of Lubricating Oil. So that part sounds pretty good. But it finishes off by saying, for auxiliary power plant equipment. So it's a very niche industry that has created this table, and it's been widely applied to a lot of other industries where these may not be the most ideal numbers to go by. To give you another quick example would be this one. At least within its title, you know the niche that it fits into. It says Worldwide Wind Turbine Gearbox Viscosity Guidelines using an ISO 320 oil. Very clear exactly where this applies to, but doesn't address wear, doesn't address contamination, doesn't claim to represent optimal performance, just gives you cautions and alarms. Again, this is only applied to work on end of drain samples, not necessarily in-service samples. If you happen to achieve these values within the normal service interval, then you probably just change your oil. But if you achieve them earlier than that, say even on the first sample, there's nothing that's going to elevate that alarm to say to you, gee, that's really unusual that you've crossed this threshold already. So this kind of highlights some of the major problems we have with all these sources. But like I said, a lot of end users, they don't go to these, they go to the lab. Now the lab has two different ways of coming up with their limits. One is static limits, which is sort of the crux of the presentation here. And another one is what we call rate of change limits, which is sort of used by some labs. And again, I'm going to pick it apart. So there's no point getting too happy about this yet. Now, when we use static limits, one of the reasons labs love static limits is because they can plug them into a computer and a computer can alarm all the sample results. So it makes for a fast and easy process for the lab to follow, and it's easy to explain when somebody phones up about a particular report and says, well, why was this alarmed? You can say, well, it's above the limit. Easy peasy. Again, these tend to work best on those end of drain samples and don't work well on all the in-between samples, the mid-interval samples along the way. Now, one of the ways you can try and make these better than just some arbitrary limits that have been determined is you can try and statistically derive them. And you can look at a lot of historical data and you can come up with some reasonable numbers, but you have to only use the end of drain samples, because if you add in the mid-interval samples, it's going to start screwing up the math. And I'll show you an example of that in a few more slides. What gets cool about doing statistical derivation is you can make it specific to a make, a model, an oil type, or a make, model, oil type combination. They get better and better that way. Now, with this concept, at least, there are still some issues. So let me show you a few of the issues. One of the issues is you may end up setting an alarm limit too high. So even if you statistically derive them, if you start changing how you do things, well, your numbers may come down and the alarm is left where it was and it may be too high. So what happens is you can have things entering into a failure mode without setting off any alarms, or by the time they set off an alarm, it's too late to do anything about it. The other issue we often see, though, is when an alarm is set too low and something is constantly an alarm. And we call this the cry wolf syndrome because, of course, we begin to ignore it because you're like, it's always an alarm and there's never a problem. So these are two of the common issues that we can get, but there are more than that. And one of the main things that leads to some of the other problems that I'm going to show you is that when we statistically derive limits, we are basing them on a multitude of assumptions, a multitude of variables that we are going to assume are fixed. And there was a great article that was written, and I'm going to show you a quote from, that established some pretty decent limits. Now, it published it in 3 different tables. So there was limits for wear, there was limits for contaminants, and there was limits for additives. And I'm not going to show you those 3 tables because they're useless. They have no value to you within this presentation to see them. What I want to show you, though, is the quote that was published after the 3 tables. So this is directly from the author within the article. He says, the warning and limit levels listed in tables 1 through 3 for wear elements, contaminants, and additives are based on, and now he goes in to qualify all the conditions. So he says, semi-synthetic motor oil, 1040, in a modern diesel engine with an oil volume of approximately 25 to 50 liters, using a certain type of fuel with an oil service of approximately 500 operating hours or a mileage of 47,000 miles. So he has qualified to the nth degree everything that determined where his tables came from. So if you don't happen to be using semi-synthetic, don't happen to be using a 1040, happen to have a different sump size, use a different fuel type, or have a different operating life, these tables are useless to you. So when we look at his table, I decided to pull just one piece of data from it. He stipulated that 100 parts per million iron was the threshold limit for wear. So using the 100 ppm iron from his derivation, I'm going to show you why he qualified all those statements. So I'm going to give you an example where sump volume plays into it, sampling interval plays into it, and I'm going to give you one other example in terms of how people misinterpret some data. But again, I'm all basing this off of 100 ppm iron in that particular application. So when you start to consider sump volume and you think, okay, I have, as an example, a gearbox, and you go, one gearbox is the same as the next gearbox is the same as the next gearbox, and you go, well, they may all do the same thing, they may all be built the same way, they may be all the same manufacturer but different models, they may all use the same oil, but if they have different sump volumes, that's going to affect the results, and that will affect where the alarms will be set. So for consideration, I give you 5-gallon reservoir that's got about 2 fingernail clippings worth of iron in it, a 50-gallon reservoir that's got nearly 3/4 of an ounce of iron in it, and a 500-gallon reservoir with a 1/2 pound of iron floating around in the oil. All three of these will measure out to 100 parts per million of iron. Now, if you had a 5-gallon reservoir on your gearbox and you had about 2 fingernail clippings worth of iron in it, you wouldn't think that was much of a problem. That would be considered perhaps normal wear or very early beginning of wear. If you had a 50-gallon reservoir with 3/4 of an ounce of material in there, that would start to look like something major. But if you had a 500-gallon reservoir and there was a 1/2 pound of iron in there, you'd be looking for a broken gear tooth. Right? Completely different perspective on it. So to show you what this looks like a bit more graphically, I'm showing you a lead up to 100 ppm alarm limit in a 30-gallon sump as the blue line, but I'm showing you the same wear at 150%. So not the same wear rate exactly, but 150% of the same wear rate, so 50% more in a 60-gallon sump. So the sump size has grown, but the wear rate has increased. And if we try and apply that same alarm limit, the black line is depicting that that alarm will not come off anywhere soon. It will take an extra few samples before we achieve that 100 ppm alarm limit. And at that point, we've experienced, like I said, 50% more wear. So sump volume plays a critical role in where you set these limits, and you can't apply the same limit on different sump volumes. Now, getting to the drain interval issue, if we assume 500 hours, like I said, I'm just pulling from that article, a 500-hour drain interval and that iron limit of 100 ppm. Well, what happens if you try and extend your drain interval? Well, if you extend your drain interval from 500 to 750 hours, that's a 50% extension on your drain interval. So you would expect 50% more wear, 50% more contamination, and 50% more degradation would be par for the course. But if you only achieved 110 ppm in that 750 hours, you'd still trigger the alarm because the alarm was set at 100. Right? So that's a bit of a cry wolf situation. You set the alarm too low. But 150 ppm is what would be or should be considered normal. So when you start making any change to any variable, having that one static limit is only going to lead you to problems. And what I usually call this one is the eventuality problem, because if you leave oil in service long enough, eventually it's going to cross any threshold you have set. Right? Eventually it will build up enough wear material or enough contamination in it, or it will degrade far enough to cross a threshold. But the issue is, in that time that it took to get there, that may not have been a problem. So we're highlighting things that aren't truly problems. We're maybe identifying when to change the oil, but we're not identifying when the machine is actually suffering. The other issue that we have is that when we set these alarm limits, we tend to miss the overall trend. Right? When we watch an oil sample go into alarm, we take a corrective action and it falls back out of alarm. Then eventually it goes back into alarm, and we take corrective action and falls back out of alarm, and we keep repeating this. And as long as the pattern repeats in a sort of a main time factor, we just think that, yeah, that's how long it takes to go out of alarm, and every time we fix it, it goes back out of alarm. We're happy. But what we don't see is that maybe that gap is narrowing, and maybe it's getting worse overall. We don't see this anymore because we just go in and out of alarm, and we're happy with that. So one of the issues I've been highlighting along the way is that most of these limits are always implied to work on end of drain samples. And I said to you at the beginning that you can only statistically derive limits if you use the end of drain samples, that you should not use the mid-interval samples. If you include those mid-interval samples, what you're going to do is you're going to drive your data to half of a reasonable limit. So consider again the data rate from that magazine article. It was suggesting 100 ppm was the limit. So let's say he got that from one data point only, from an end of drain sample point only. Well, if he gets one data point at 100, the average for all that data point works out to be 100. But if he has two data points, the second data point would be the mid-interval sample. So at mid-interval, you would expect a mid-result. So say they were 50 and 100. Well, your average drops down to 75 now. If you had three data points along the way, so two mid-interval samples and your end of drain sample, and again, just smoothing the data out here to be very linear, your data points would be at 33, 66, and 100 ppm. Well, the average for those three values works out to 66 ppm. So you see how my average is dropping just by including more data in between a normal 100 ppm end of drain sample and just adding more mid-interval samples along the way. And just to show you one last example, if we double it again, give you 6 data points along the way. So now we have 16, 33, 50, 66, 83, and our final end of drain at 100 ppm values. The average of all those values works out to 58 ppm. If we kept slicing and slicing and slicing this, eventually we'd reach 50 ppm as our average value. So my point is, statistically deriving your limits may be great, but you can only use the end of drain samples. You can't use the mid-interval samples. But that means you have nothing that works for the mid-interval samples. So if we've accepted what I've explained here is logically only using the end of drain sample, how do we alarm a mid-interval sample? So assume that we've reached 50 ppm after 250 hours, right? That would seem fairly normal if we stick with our 100 ppm is achieved after 500 hours, as pointed out in that magazine article. So we assume that is normal. Well, no alarm is triggered if the result jumps to 90 though, because we've set our alarm at 100. So 50 is what's considered normal, but we wouldn't even alarm 90 because we've applied one singular limit to it. If we happen to go over 100, we don't elevate the alarm even though we only run for 250 hours. And we just sit there and say, no, the limit's 100. If it goes over 100, alarm it. Well, it's still alarmed, but we don't elevate the alarm to say, wow, you've achieved this much sooner than you normally would. So it gets very difficult to come up with a logical mid-interval limit. Even if you use fixed intervals and stick with, I always sample at 250 and I always sample at 500, very hard to come up with limits that are going to work on both sets of numbers and identify when to apply which limit, all that kind of stuff. It just gets complicated. So just again, to show you something graphically, assuming a normal trend working itself to a 100 ppm limit is the blue line, but I'm showing you the wear and contamination, whatever we're looking at here, doubling for the same sump size for the same interval. And all you notice is that the alarm comes on sooner, right? It doesn't elevate itself, it just comes on sooner by 1 or 2 samples. But we've got double the wear, but it doesn't happen at half the interval. So the issue is that we don't identify different severities of problems. We don't see that a static limit is really helping us identify when one machine is behaving much worse than another machine. All we get is a threshold has been crossed and a report is an alarm. And if the first alarm is a caution or a marginal or whatever you want to call it, we don't tend to react to that until we see that critical warning. And that critical warning just simply appears on maybe the next sample, and then we take action. But we don't realize it happened twice as fast or at twice the rate. Now, one last thing I'd like to point out is what I call perceived value versus actual amount. And this is one of the things that's sort of the hallmark of limit problems. This crops up time and time again and helps highlight the issue that people have when interpreting a lot of the wear and contamination results. So my example to you is a 2 part per million change on a single wear metal. So again, let's consider iron because I've been working with iron. Well, when people see iron go from 1 ppm to 3 ppm, a lot of folks will tell me, well, that's a 200% increase. It has tripled or some phrasing like that, and they get very concerned about it. But if we consider that it's going from 11 ppm to 13 ppm, now that's only an 18% increase. And if you were to look at it as 101 going to 103, it now drops to a 2 ppm increase. The point of all 3 of these examples is if we're talking about the same sump size for all 3 of those examples, it's actually the same amount of physical material that has created that increase. So why I'm showing you this is when you read your data, imagine that you added 100 to everything. So when you're reading your data and you're looking at 7 going to 9 or 1 going to 3 or whatever the low levels are that we're seeing, imagine if it was 107 going to 109 or if it was 101 going to 103, and ask yourself, how would you react then? Right? When we look at these changes, we often perceive them as mathematical changes. We look at the 200% increase or the 18% increase, and not how much physical material did it actually take to do it. So a 2 ppm increase is still 2 parts in a million. It's not very much material. It's generally, unless it's a very large sump that we're talking about here, generally not a lot of actual physical material causing these changes. So we tend to overreact. So let me show you that perceived plot here. So there's some data showing a general 1 ppm change, and then all of a sudden a 2 ppm change. And on that graph on the left-hand side, it looks like a pretty substantial increase. Now let me show you the exact same data at the exact same levels, and all I'm going to do is change the scale on the graph. So rather than have the graph start at 10 and work itself up, I have it starting at 0. And now you think, well, that's pretty normal, that's pretty smooth. And if we started adding 100 to all these values, it would look even smoother. So that's what I'm always trying to explain to people when they're reading these reports, is don't overreact to these small changes. Ask yourself, what if it was at a much higher value and it was the same overall change? Would you react differently? And most people would agree they would react differently. So I go, well, that helps explain what we're seeing here. So those are the 3 different problems I wanted to show you inherent with static limits. So when people see these problems, one of the things they come up with as a way of overcoming all of these issues is to simply use rate of change. Rate of change is what we sometimes call time-dependent limits. It's where time is taken into account and therefore actually negates some of those problems. Now, it does rely on reporting of hours or mileage or something, and it actually now needs many mid-interval samples for it to work properly. So this sounds like the right fix. This sounds like something that's going to work for us, because if you remember the history I began with and said we didn't have that in the initial stages, it's something we've inherited over time. You go, well, rate of change seems like it incorporates that and can use that. Well, some of the downsides of rate of change is that every time we top up, we're going to skew the results a little bit, and we still have built this calculation on a lot of assumptions. And those assumptions, as sound as they may seem when I say them to you, I'm going to prove to you most of them are wrong. The main assumption that we work with is that rates of wear or contamination follow what we call the snowball effect, meaning the worse it gets, the faster it gets worse. The other assumption that we use is that values often will reset to near zero values or new oil values every time we change the oil. Well, both those assumptions are driving why rate of change simply doesn't work, because those assumptions are completely wrong. So there was another magazine article that was published, and in it had this table here, which is or chart, I should say. It's a pretty decent chart as long as you know what it's telling you. So allow me to explain it to you, and then it'll make a bit of sense from what looks like a bit of a mess here. If we look at the blue line, the jagged blue line, what that is a plot of the average iron value. Now, iron is depicted on the left-hand axis, for the service intervals, which is depicted on the bottom axis. So the longer the service interval is, the more iron there is. Well, that kind of makes sense. The smooth blue line is simply the best fit line for the jagged blue line. The other line we should pay attention to at the moment, though, is the red line. Now, the red line is the number of samples, as depicted on the right-hand axis, for the service intervals, again depicted on the bottom axis. So what this means is that at approximately 250 hours, where we see the big spike in the red line, it means we've got a lot of samples supporting that data point. Well, if you look at the data point at 250 hours, it has an iron value of approximately 12 parts per million. So that shows us that the average iron we would expect in, and if you read the title of this chart, it says it's for a Caterpillar 3406 engine, the average iron that we would expect in that engine at 250 hours is approximately 12 parts per million. Well, if you look at the red line, there's another little spike way over at 500 hours. Now, at 500 hours, that happens to be exactly double the drain interval, or sampling interval, I should say. At double the sample interval, what would you expect the iron result to be, knowing it's 12 at 250? Well, 24 at 500 seems like a pretty reasonable guess as an answer to that question. But if you look at the graph, it shows you the value is closer to 21. So as you try and rectify this anomaly in your head and go, why is it only 21 if it was 12 at 250? Take a look at where the graph begins. The graph doesn't begin at 0 parts per million iron at 0 hours. It begins a lot closer to 7. And you go, why is there approximately 7 parts per million at hour 0? Well, that is something that we generally refer to as oil hang-up. It's the amount of oil within a machine that will not drain out during a normal drain procedure. So this is an engine. Many of us drive our vehicles. If you've ever witnessed the oil change on your own vehicle, most passenger vehicles take about 4 quarts or more of oil. And if you drain the oil out of an engine, you don't get all 4 quarts back. You get 3 and a bit perhaps. But there's a residual amount of oil that is hung up, that's why we call it oil hang up, within the machine that doesn't come out. Now, statistically, this has been shown to be upwards of 25% of the original system volume can be attributed to oil hang up. But here's the interesting thing about this 25% by volume. If you consider the residual oil left over after an oil change, ask yourself this question: does that oil look exactly like all the other oil that came out? Does it look potentially cleaner than the oil that came out? Or does it look like the nastiest, sludgiest, gummiest, dirtiest portion of the oil that came out? And hopefully you're picking that last answer, that the residual oil is in fact probably more contaminated and contains higher amounts of wear material in it than the oil that did drain out, because it's the last sludgy bit that's left behind. So if you start to appreciate that that is the case, I can share with you that, again, statistically, it's been shown through graphs like this one here, that oil at hour 0 after an oil change can retain upwards of 40% of what was there at drain. So instead of an oil drain reducing our wear and contamination values to 0% of where they were at drain, like I said, it can reduce them to only as high as 40%. So when you consider that it was 21 ppm at 500 hours and we drained the oil, and we're extrapolating a little bit here, but we're suggesting that the data shows 7 ppm at hour 0, we see about 30% right there. That in this particular graph, we've got 30% residual value starting at hour 0. So if you can appreciate all that, now imagine if we apply rate of change to this. Now, how you arrive at rate of change is you take your iron value and you divide by the hours of service. So when you do that, you end up with that green line. Now, that green line shows you the average of the iron content divided by the hours of service. So the blue line divided by the bottom axes gives you the green line. Well, what you notice about that green line is the trend on this is not flat. And also not increasing. If anything, it's decreasing. You go, well, why is this? Well, first off, hopefully you also notice that it starts off quite high and dramatically drops. Well, that's because if you try and divide a number by a near 0 hour value, you're going to get a very large value. So right away, we've identified that having this best fit line run through 7 ppm at hour 0 is going to give us some mathematical issues. So what if you get smart and you say, look, that 7 parts per million that it starts with, I don't care about that 7 ppm. That 7 ppm I can never get rid of. So why don't we do, and this is normally referred to as a baseline correction, why don't we take the 7 ppm that we have at hour 0 and simply subtract that from all future values? Because we just want to see how much it's increased since the oil was changed, not how much is there overall. Well, if you get clever and do that, you're going to arrive at the purple line. So if you take a baseline corrected version of the blue line and divide by the hours, the bottom axis, you get the purple line. And the purple line is the most intelligent rate of change we can possibly apply. And if you look closely at that purple line, again, if you notice something about that line, it is not increasing. And it's not really flat. It actually still follows a slightly downward trend. So right away, we can take a look at those two assumptions we began with and say, the rate of change doesn't increase, and we've already identified values don't reset to new oil values at an oil drain. So rate of change has too many issues. So the only issue we have is to come up with something that works. Well, the something that works is trending, and that's the end of the presentation here, is to talk about trending. So trending is a very simple way of interpreting data, and you can use the simplest of tools. Linear regression is one of the simplest ways of looking at a trend. Now, to do this, we need a bit of a history. So as few as 3 samples can give us enough of a history to start doing something with this. And at TestOil, we wait for that 4th sample. That's how we do it. Sample something 4 times in a row, we can turn on linear regression, and we can now look at a predictive path of where that data is going. So all we need to do then is look for a significant deviation from this projected trend based on the previous 4 pieces of data, using a linear best fit, and say, if it's outside this value, set off the alarm. Now, the typical ways that this can be done is simply by using standard deviation. So I won't get into all the complicated math behind that, but it's pretty simple statistics that 1 standard deviation includes the bulk of the data, 2 standard deviations starts to indicate some of the outliers, and 3 standard deviations where the greatest concern is placed. So generally speaking, when you start setting alarm limits, you consider 1 standard deviation to be okay, but anything that exceeds 2 is kind of a caution, a marginal, and anything that exceeds 3 is definitely warranted to be critical. The nice thing about linear regression is it can work in harmony with any established limits. So even if you've been given limits from your OEM, your loop supplier, or industry, or if you statistically derived your own, whatever the source may be, you can still use them in conjunction with trending. So let me show you all the examples I've already shown you, but with trending turned on. So trending is going to appear as a bit of a blue haze. That's your 1 standard deviation as what's being shown there. So even if you set your alarm too high, you'll notice that this data has gone outside the best fit line, which is the horizontal blue line in there. And the haze that's around it is, like I said, the 1 standard deviation. So it is shown as exceeded that significantly, and we can alarm this. Now, if we set our alarms too low, well, you notice that that data that's now being shown fits within the blue haze. You're rewarded now for consistent data, regardless of where the alarm's been set, and it will turn off the alarm. It will say, no, this is within 1 standard deviation. Everything's fine, leave it alone. In the case of the eventuality, as long as it follows a fairly predictive path, no alarms get set off because it says, no, that is expected, that is normal. For continued service, you're going to get continually higher wear, higher contamination, and more degradation. The trends one, when we missed out on an overall trend, this one, again, can capture it because it can show it to you, because you can see the best fit line is actually rather steep. Even though the data looked like it was fairly horizontal, we can pick out what that trend might look like, but we're rewarding that trend and saying, no, it's following a definitive path. So all of the examples I've already shown you, you can see how trending helps turn off a lot of nuisance alarms and only alarms those things which are really necessary. But here's where trending really starts to shine. Look at this example and see the data. The data is well below alarm limits. The data has actually been decreasing, but the data has taken a sudden turn for the worse. Now, when humans generally interpret this kind of data, they make one fatal error. If you notice, the data set starts with a value at 8 parts per million, then it drops to 4 and goes back and forth a little bit, and it eventually drops to as low as 1. Sample number 6, the value is 1. Then it climbs to 3 on sample number 7, but by sample number 8, it has jumped up to 7. Now, with trending turned on, it has identified that particular last value as out of trend. As you can see, it's exited the blue haze around the best fit line, so it's being alarmed. When humans interpret this, though, one of the things they see is they go, well, why would I alarm it at 7? In previous history, it was as high as 8 and the machine didn't fail. So why would I care about 7? The point is, this is a huge point. It's not that 7 means it's going to fail. It just means it's outside of trend. Because if it's 7 now, where do you think the next data point is going to be? It's going to be way higher on sample number 9. So we're actually being predictive at this point. It's not to say that 7's a problem. It's saying 7's indicating there will be a problem. That's the big point here. But normally when humans see a value like that, they would say, well, I wouldn't alarm that. Turn that alarm off. That's 7 ppm. That's not worth alarming. But it is. It is because of the trend that preceded it, not because of its absolute value. Another issue that we have is this type of trend. As you can see, the data begins at about 7 and it gets as high as 11 and goes back and forth a few times, but the very last data point has dropped to 2. And again, normally when humans interpret this, they go, why would you alarm something that shows that it's gotten so much better? The issue is that we don't know that it got better. We only know that the value is lower. It's an assumption to say it got better. Well, what if we're measuring a lot less iron now because the iron particles have gotten larger and gone outside the scope of measurement? Or what if they're now being trapped by the filter and aren't showing up in the oil sample? There's a multitude of scenarios where this data, though it looks better, in fact may indicate a worse problem is taking place. So with trending, we can identify something has gone off trend, even if it's gotten better or perceived as better, and still say this is worth looking at to show there might be a problem. Now, one of the things that we often talk about in the world of reliability when we think about oil analysis is we describe oil analysis as a predictive technology. And we come up with this classification because the 4 main strategies in the world of reliability are reactive, preventive, predictive, and proactive. Now, reactive is always the if it breaks, fix it. Preventive is the change it out before it fails. The predictive is anticipate if it's going to fail, and proactive is kind of the best of all worlds, whereby we utilize history, just have done root cause analysis as an example, and try and figure out some both preventive measures and some predictive measures together to help prevent future failures. Most people feel that oil analysis falls into that predictive category, that oil analysis is performing a measurement, therefore it's predicting a failure. But what I like to always, kind of have a discussion on is I actually think most people use oil analysis in a reactive way. Most people get oil analysis reports sent to them as long as they're not in alarm, they don't do anything. Only when they're in alarm do they actually do something. Well, waiting for something to go into alarm is really letting it break and then fixing it. It's kind of a reactive strategy. To be predictive, what you'd want to see is where the trend is going. Even if it's not outside of trend, even if it's not outside of alarm, where is the trend going? And that's the neat thing about trending. Trending can predict where the value is going. And if you can see that, well, currently it's not exceeding an alarm on sample number 7, but by sample number 8, I am predicting it will be an alarm. I have now taken oil analysis and made it a predictive technology. I have looked at my reports and looked at my trending and said, I can tell you by the next sampling interval, that thing will go into alarm. So what can I do to mitigate that from happening, or what can I do to anticipate its occurrence? I have now taken oil analysis and truly made it predictive. That's how it was meant to be used. That's how it was used in the beginning, back in the 40s and 50s. But like I said, we've kind of lost sight of that now. Nowadays, most people just wait for a really bad report to cross their desk before they schedule anything to be done. And that is pretty much a reactive way of thinking. And let's face it, as I've hopefully shown to you throughout the presentation, if you've relied on that report being in alarm based on some arbitrary limits come up with from who knows where, chances are those alarms are wrong anyways. So you're chasing your tail on things that don't exist, and you're missing out on things that you could have predicted would have happened long before they did. So in summary, trending is but one part of the interpretation. I'm just suggesting is the most substantial part. The nice thing about trending is it can work on a one-off sample as well as a large fleet. So it doesn't need to have many examples of the same machine or many commonalities between some volumes and operating conditions and operating times and all that. As long as you consistently sample from the same machine at consistent intervals, you can turn trending on and figure out if the machine is behaving in a way that makes sense. So trending does not require make model information. It doesn't require reporting of sump sizes. It doesn't require reporting of makeup oil values and all these kinds of things that seem to be quite elusive to most end users. So that's a benefit. It works on the end of drain samples and the mid-interval samples, which is something you can't say is true for all static limits. It can work entirely independently or in conjunction with limits. So if you're still bent on using some limits, or if you're being given regulatory or warranty related limits that you cannot exceed, trending can still use those. It's not a give or take, it's not a one or the other. They can work together. But the most important thing is that trending is far more, and I emphasize this word here, predictive than just limits. Limits really put you back into a reactive maintenance mode, and that's not a good place to be. Trending puts you in a position to be predictive, and if you're predictive, that generally works out to significant cost savings on either reducing the severity of impending failure, or possibly, I don't like to emphasize this one too much because it's kind of difficult, but sometimes you can even mitigate a failure. I always like to stress that I find that the world of reliability is mostly bent on reducing severities of failures, not the number of failures, because if something's going to fail, it will eventually fail. So you can't prevent it from outright failing. But what you can do is try and reduce the severity that it will fail at and be as prepared as possible for that failure, so it costs you as little downtime, parts, labor, all that kind of stuff. So with that, I have reached the end of the presentation, so I thank you all for listening. If you do have any questions, please use the question function or the chat function within your go-to toolbar. Otherwise, you can always email me later, but I'll turn it back over to Taylor now and see if there have been any questions that have been submitted along the way. So once again, thank you.
All right, thank you so much, Evan. We do have a few questions here. Okay, the first one says, how about a mid-range limit? First a warning limit, then a higher limit to warn of approaching failure. My point is that why would we wait for a failure limit to trigger action?
Both good questions. So the first question about a mid-range limit. A mid-range limit, again, you could statistically derive both a mid-range and an end-of-drain limit if you had the supporting data to do so. And that may be fine, but now you're trying to apply two different limits, so you have to properly identify if it's a mid-interval or if it's end-of-drain sample, which doesn't sound complicated, but again, knowing how most laboratory LIM systems work, that begins to be a bit complicated, but it can be done. So if your system can support that, or if you're importing your data into your own CMMS software and it can support it, that may be viable. And that works to a point. But again, as I tried to point out, no matter how well-intentioned, well-thought-out, and well-derived any statistical limit might be, it still has some inherent issues where if you change any variable, it now becomes invalid. What was the second part of the question, Taylor?
All right, let me pull that back up here. Okay, the second part there was, his point was, why would you wait for a failure to limit a trigger in action? And should we ask the lab to perform the trending analysis or do it ourselves?
Okay, well, there's actually three questions. I misinterpreted that. Yeah, so in terms of the second question, no, I don't want to wait for a failure. Like I said, I'm trying to put oil analysis into a position to be predictive so that we're not setting an alarm that indicates when it's at alarm, it is at failure. The point, hopefully, of doing a statistical derivation of any limits is to identify the inflection point, or what we sometimes call the PF interval, where the potential failure can be identified, not where the functional failure is identified. So hopefully that's a strong enough answer for the second question. But the third one, the whole issue is, who should do this? It's great when the lab can do it, because obviously they get the first pass at the data. And at TestOil, we of course do this. So I would always be saying, yes, let us do it. But if you're dealing with a data export and you're wondering how it can be done at the end user level as well. Like I said, it's not complicated. It doesn't require any strong algorithms. Like I said, something as simple as linear regression can do it. So it could be done either or. I would rather see it done at first pass. I would rather put the onus on the lab to identify the trends. They're generally the ones who've got better access to this type of software or computing capabilities, but you could do it at the end user level. So again, hopefully that's enough of an answer for you. But yeah, I would want the lab to do it, because I would want them to incorporate their recommendations based off trending rather than based off static limits. So rather than handing that over and then having the customer trend it again, doesn't seem like a practical way of doing things. Hey, what was the next question, Taylor?
All right, it looks like there's a few more questions here that would be better answered via email. I would like to thank everyone for joining us today, and thank you so much, Evan, for presenting.
Great, thank you.